are very useful ways to determine how good an experiment is going to be before you do it. So it's very useful in experimental design. It's also useful for MCMC because it basically tells you what shape of likelihood surface you expect to get from a given experiment. So it's useful both for designing an experiment so that you get nice small error bars, but also useful for MCMC because you need to find a proposal distribution. And actually the Fisher matrix is quite a good way to give you a good proposal distribution because it has roughly the same shape as the target distribution that you're trying to sample from in MCMC. So you can do generally very quickly and very easily work out what the expected shape of the likelihood surface is, and then you can use that as a proposal distribution for MCMC. It can be quite efficient. So let's just have a look at how we analyze parameter errors. If we let's assume uniform prior, so the likelihood and the posterior are basically proportional to each other. So the errors that we would get, which would come from the posterior, we would just use the likelihood to tell us. So let's assume that we have a likelihood surface which is very simple. It just has a single maximum. It doesn't have many modes. And concentrate on what the likelihood surface looks like near the peak. So if you do that and you do a Taylor expansion around the peak, then the log likelihood will be the peak value at theta naught. And then the Taylor expansion, which gives you, the first term disappears, the term which will be d log L by d theta, because at the maximum that is 0. So the first non-zero term in the expansion involves the second derivative of the log likelihood. And this thing is, depends on, we've got two indices here, so this is basically a multivariate object. So if we then take that approximation, let's truncate the Taylor expansion of this term here, so ignore everything to the right, and then exponentiate the expression, then that ends up looking like a Gaussian. Okay. So the Gaussian, this matrix in here is called the Hessian matrix, and it's essentially defined by this equation. It's minus the second derivative of the log likelihood with respect to the parameters. So if it's an n-dimensional parameter space, then this matrix will be an n by n matrix. So that's called the Hessian matrix. That's what you would get from an experiment, an approximation to the curvature of the surface near the maximum. So, if the Gaussian approximation for the shape of the likelihood surface is a good one, if these extra terms are not particularly important, then the errors and their correlations are determined entirely by this Hessian matrix. So, for example, if you keep all of the parameters fixed except for one, then the error will be there's a mistake here, actually. This should be 1 over the square root of the alpha component of the Hessian matrix. So that would be called the conditional error. So that's keeping all other parameters constant, but just allowing one of them to vary. Don't quote this error because it's very rare that this error is the relevant one, and we'll see later what the right thing to do is. Okay, so that's an actual likelihood surface given some data. So if before you collected any data, you want to work out what to expect from this, what you can do is to work out the expectation value of this Hessian matrix before you've collected any data. So with certain assumptions, you can calculate this object just based on the data that you're intending to collect and its statistical properties. So this will give you an idea of what you're going to get out. It won't be exactly what you get out from a given experiment, but it should be give you an indication. So the advantages of doing this are that you don't need any data. So it's a very quick thing to calculate. You don't need to simulate the experiment. you can get all of this without any data. You only need the statistical properties of the data for a given model. So for example, for Gaussian fields, we know that Gaussian data, what Gaussian fields, but any data which is distributed in a Gaussian way, which by the central limit theorem could be a very wide range of experiments that would be Gaussian. The only things that you need are the covariance matrix, which may depend on the parameters, and the mean, which will in general depend on the parameters. And all of the statistics are determined by the mean and the covariance, so it should be ordinary. So the alternatives to this would be to generate simulated data that simulates your experiment, or your observation, and then run, say, a Monte Carlo Markov chain on it, and then get some likelihood surfaces that way. So this is much faster. The disadvantage is that it assumes that the two things. Well, one thing really, it assumes that the likelihood surface is a Gaussian. Now, if you go very close to the peak, then it will be Gaussian, very close to the peak, but actually you're interested in how the likelihood surface behaves when you go down to some fraction of the peak value. So that may or may not be a good approximation. It depends on the experiment. Here's an example which compares Fisher matrix expectations with simulated data, and never mind what the experiment is, but just the colours show the output from a MCMC, and the contours give you, the black contours give you the Fisher matrix results. So you can see that, broadly speaking, it does a reasonable job in this case. In some cases, it's pretty good. In some cases, it's really not quite so good. So, don't treat it as being a very precise science to do Fisher matrices, but in most cases, it will give you a reasonably good idea of the sort of error bars that you're going to get from an experiment. So let me just show you how this works for Gaussian data, because it's such a common situation. You can compute the Fisher matrix. As I mentioned, it depends on the covariance matrix and the mean only. And let me sketch out a calculation. You can see the full details in this paper if you want. So if you take the log of the likelihood, then the exponential just turns into this, but the determinant outside becomes the log of the determinant of C. We want to know the expectation value of the second derivative of this, so if you differentiate it, C is the covariance matrix, D, we can sometimes refer to this as the data matrix, which is just this part, x minus mu times x minus mu transpose. So if this has an index I and this has an index j, then the element dij will be given by this. So that's sometimes called the data matrix. The notation I'll use is that a comma indicates a partial derivative with respect to the parameter. So an exercise for you, if you like doing these things, is there's various weird matrix identities that you need to do the calculation. So if you like doing this sort of thing, you might like to prove these strange things. You might wonder what the logarithm of the matrix is for a start. So if you fancy doing it, if you don't know what the logarithm of the matrix is, then come and ask me. So if we differentiate this, then we firstly replace the logarithm of the determinant of C by the trace of the logarithm of the matrix, and then we do the differentiation. So you just use the chain rule for this. So that gives you the first derivative. You then differentiate it again to get the second derivative. You get this. I'm not going to go through the details of this. And then you take the expectation value. And you end up with a relatively simple expression for the Fisher matrix for Gaussian data. So it has these two terms. The second term is often the one that's most important. If your covariance matrix doesn't depend on the parameters, then this first term vanishes and you just have the second term, which depends on the derivatives of the mean signal with respect to the parameters. So if you have a theoretical model where the mean, let's say, the TNE power spectrum depends on the parameters, then these involve the derivatives of the mean. So this is a very useful expression. It's used very widely because you don't have to explicitly do the differentiation of the log of the likelihood. It's all done for you. It's given by this. Okay, so let's just explore what you get out of this. You get a matrix out of this, F alpha beta. The conditional error, I make the same mistake again, the conditional error should be 1 over the square root of the beta component of F. And that conditional error, as I say, is rarely useful. It is occasional, it is rarely a relevant one. What is usually the error that you should quote is the marginal error, because you don't know any of the parameters precisely. So the uncertainty in one parameter is determined to a certain extent by the uncertainty in the others. And that's given by the square root of the beta component of the inverse Fisher matrix, and I'll show you where that comes from later. This error is no smaller than the conditional error, and it could be, in many cases, it can be very, very much larger. If you have a high-dimensional system with many parameters, and you calculate the conditional errors, they can be very much smaller than the marginal errors, yeah.
These may be a question, what's the difference between a marginal error and an additional error?
Okay. I'll answer that on the next slide, because I've got a diagram on there which will help. So, basically we end up with something like this. This is the prediction for the shape of the likelihood surface. So it's a two-dimensional probability distribution, or expectation of the probability distribution. And because of the assumptions, these are always elliptical, because we're assuming a multivariate Gaussian. So we can ask various things, such as if we know the value of the vertical parameter, so we set it, let's say, on the axis here, then we can ask what would be the uncertainty in the parameter along the x-axis. So if you ask how along this line, there's a probability along this line, the likelihood, and you can ask what's the range that contains 68% of the probability, for example. So that range would be from here, where this solid line cuts the axis to here. So this would be the 68% probability if you assume that you know what the value of y is, so you know the y parameter, then the 68% range would be this. Now, if you don't know what the value of y, theta y is, the vertical one, which is the normal case, then the uncertainty on x is actually larger because of the probability that's out here and out here. So if you marginalize, if you were to integrate vertically to get a Gaussian probability distribution, it would be broader than the Gaussian that you get if you were cut through this line. Is that clear? So, Leacher mentioned this earlier on. If you end up with some data and you have some contours of chi-squared and they're Gaussian-like, then what should you quote? And this chapter of the numerical recipes book basically has everything that you need to know. So, whenever you need to do this, go and have a look at that. And I think you can get it online, I think. So there's a table which tells you, depending on how many dimensions you're working in, how far down, what change of chi-square from the peak value you need to go to include, say, 68% or 90% of the probability. So, for example, in 2 dimensions here, if you want to include 68% of the probability, then you need to go down to delta chi-square of 2.3, which is the dashed line here. So 68% of the joint probability is within that dashed ellipse. If you marginalize, then the range that contains 68% of the, let's say, 68% of the probability of the parameter in the y direction, then it's given by the projection of this ellipse onto the y, onto the x0 axis. So that's from here to here. So this applies, this is quoted in terms of chi-squared. If you calculate a likelihood, which may not be chi-squared, it may not be quite this because of terms that may be outside, then you would apply these numbers to minus 2 twice log L. These all assume this is a Gaussian distribution. If you do some actual experiments and they don't look Gaussian, then you should do something different, and you should numerically find the region which is above the, say, 68% of probability. But whatever you do, make sure that you say what your errors are, because sometimes people just say the 1 sigma error bar is such and such. And I have no idea whether it's the 1 sigma, whether it means that 68% of the probability of both parameters lies within that range, or the probability of one parameter lying in the range. So make sure that you specify, if this is Gaussian, to say that if you say it's 1 sigma, that refers to the joint distribution of 2 parameters or a single one. Okay, so this result of using the inverse Fisher matrix to give you the marginal errors is something which is just quoted everywhere, and many people know what it is, but I've never been able to find a proof of it. So let me give you one, because it's such a central result, it just doesn't seem to be easy to find. So we can prove this result, very important result, using characteristic functions that we saw earlier in the week. So if we define the characteristic function as the Fourier transform of the probability distribution, then if we regard this now as this is now the expectation value of the e to the minus I k dot theta using the probability distribution P, then it's easy to show, to generalize what we did earlier in the week. If you want to look at the correlation properties of the parameters, then each time you want to, if you want the correlation properties of a number of parameters, you simply differentiate the characteristic function with respect to ik for each of the parameters that you're interested in. So if we differentiate with respect to θ1, then that will bring down a factor of minus I k1 and so on. So if you differentiate this some number of times with respect to these k vectors, and then evaluate this quantity at k equals 0, that will give you the expectation value of whatever product of features you want. So the one that we're interested in here is the covariance of the parameters. So if we assume 0 mean, then the covariance is just given by the expectation value of theta alpha, theta beta. That will be a matrix. Diagonal parts will give you the variance of each of the parameters. The off-diagonal terms will tell you about the correlations between them. So in the previous slide we had an ellipse which was at some random angle. If the ellipse is aligned with the axes, then the off-diagonal terms are 0. If they're non-zero, then that means that the ellipse is oriented at some angle. Okay, so the covariance properties of the parameters are given by the second derivative of the characteristic function. We've approximated the likelihood by a Gaussian function, so for 0 mean it looks like this. With the Fisher matrix, this is the expectation value involves the expectation value of the log likelihood. So we have the Fisher matrix in here, theta here is the vectors. So we have in general a Fisher matrix which has off-diagonal terms, but it's a matrix which is positive definite, and symmetric. We can rotate it into a coordinate system where it becomes diagonal, and that's what we'll do. So if we rotate it with the rotation matrix R, It's a rotation matrix, so the inverse of R is the same as the transpose. If we do that, and we then introduce this new variable psi, which is linear combinations of the parameters, then this quadratic form in here, theta f theta, becomes psi transpose R f R transpose psi. And by doing this diagonalization, then the matrix in the middle here is just a diagonal matrix. So we just do the standard diagonalization of the matrix at this point. So lambda is a diagonal matrix, and that's the thing in the middle. So then the characteristic function we can write in terms of psi. So the quadratic in the exponential becomes this object. This is the exponential term, which is written in, it's e to the minus I k dot theta. So I've replaced theta by R transpose psi. I've also changed the integration from theta to psi. There's a Jacobian involved in making that transformation, but because it's a rotation, that Jacobian is unity. So dm theta is the same as dm psi. Okay? So that's the expression of the characteristic function in terms of these new variables. And if I define a new k vector, which is just r times k, then this exponent simplifies to this. Okay, so now we have a characteristic function which is a little bit easier to deal with, because lambda is a diagonal matrix. Then this m-dimensional integral factorizes into m individual integrals. Each component can be done easily. So this quadratic form is just psi I squared times lambda I. So we can do each of these individually. They're just Gaussian Fourier transforms. You know what the transform of a Gaussian is. It's just another Gaussian. So each one individually ends up giving you a contribution like this. So this applies for every component, and the k here would be the relevant component of k. So we can then evaluate what the characteristic function is. It's just e to the minus, since we end up with a product of terms here, that ends up being a sum in the exponent, the sum of ki squared over 2 lambda I, or if we want to do that in matrix form, that's k transpose lambda to the minus 1 k. And that, if you then transform that back from these new k vectors, capital K vectors, back to the original ones, that ends up being little k transpose f to the minus 1 times k. And that follows from the fact that if we substitute the lambda in here, lambda is lambda to the minus 1, and we rewrite the k, capital K's in terms of lowercase k's, then this term in here, you go back to the rotation, that's ends up being f to the minus 1. Okay, so by doing that rotation, then we can then write the matrix, the characteristic function in terms of f to the minus 1, and then you can work out the covariances just by doing the differentiation on this object. So you find the covariance matrix is just the inverse of the Fisher matrix. Okay, so that's a result which is used all over the place. Everybody just quotes the square root of f to the minus 1 as the diagonal parts as the variances. Okay, so what this shows is that the covariance of the parameters is the expectation value of this is the inverse of the Fisher matrix. So we'll use that later, so remember this for later on. Okay, one thing that one sometimes has to do is you may be given a Fisher matrix which is written in terms of a particular set of parameters, and you may want to work out the Fisher matrix in terms of a different set of parameters. So one common example of that is in the CMB, then one of the parameters is usually the amplitude of the primordial power spectrum, usually given the symbol A. The amplitude of the power spectrum is very often used as a parameter in the CMB, whereas in large-scale structure, the term that gives you the amplitude is often sigma 8. Okay. So those two are not quite proportional to each other because, well, they are proportional to each other if you keep everything else fixed, but sigma 8 has some dependence on the shape of the power spectrum, so it also depends on omega matter and so on. So there is a transformation from sigma 8 from A and omega matter and so on to sigma 8. So sometimes if you're given a Fisher matrix, say in terms of CMB parameters, but you're doing an experiment in large-scale structure, you may want to transform your variables from A to sigma 8. So how do you do that? Well, we can do an expansion of the difference between a new parameter, say pi, around the maximum, then by the chain rule, a small separation in the new parameter is given by d psi I by d theta j times the distance in theta from the maximum. So if you differentiate, we want to work out the Fisher matrix in the new set of parameters. So if we take the log likelihood and we differentiate with respect to one of the original parameters, then by the chain rule we can write it like this. If we differentiate it again, then we get two terms, one from differentiating this first term and one from differentiating the second term. So the first term just gives us another transformation, and the second term comes from differentiating the second term. So if we then take the expectation value of this to give us the Fisher matrix, then the second term disappears because we evaluate these derivatives at the maximum, and the expectation value of the derivative of the log likelihood is 0 at the maximum. So this second term disappears, and we just have this first term. So the first term, you'll notice that the first term here is just minus the Fisher matrix in the with respect to psi, and we have these two matrices that give you a transformation. So we can write this in a matrix form compactly, but if we take minus this, then the left-hand side is just the Fisher matrix in the theta system. And then if you reorder these so that you can have the order of the indices correct, this turns out to be the transpose of B, where B is this matrix, times F in the psi system times B. So it's relatively straightforward if you're given a Fisher matrix in terms of some parameters to change into a different set of parameters just by a couple of matrix multiplications that determine by the transformation of one parameter system to another. Okay, any questions so far? Okay. So what other things can you do with Fisher matrices, or what other results are useful? Well, if we have some independent data, so if you have two independent data sets, then things are very simple, because we know that the probabilities then multiply, so the likelihoods multiply. So the log likelihoods simply add. Then if you differentiate them twice and you take the expectation value, then those just add as well. So that tells you that for independent data sets, then the Fisher matrices just simply add. Okay, so that's useful if you're doing two completely different sets of experiments, one in the CMB and one in 21 centimeter, say, and you can just simply add the Fisher matrices. One other thing is that if you have a set of modes, if you work out the Fisher matrix for a single mode, for example in the CMB, you might work out the contribution to the Fisher matrix from a single ML mode. That in general won't depend on M because of isotropy, so it's a function of L. So the different L and M modes are independent. So you just add them up. So for any given L, you have 2L plus 1 different M modes. So if you work out the Fisher matrix for a single mode, data set that consists of a single mode, then the Fisher matrix for all of the n modes with the same L will just be 2L plus 1 times the mesh matrix that you had. Basically, you just have 2L plus 1 of these. And then if the L modes are independent, then you just simply add up those sum over L. So sometimes you may see Fisher matrices for the CMB, you may see sums over L of 2L plus 1 times some object. That's why. Okay, so if we do combine some data sets, sometimes you get some strange looking results. Sometimes they're quite pleasingly strange. So this is an example from, I forget exactly what, weak lensing plus something else. I can't remember what the two data sets were, two independent data sets. So these are Fisher matrices for the individual ones, which are the blue ones, and the green ones. And then the combined data set coming from adding the Fisher matrices. And this looks a bit odd, because it looks as though one of the data sets confines you to this region, the other data set confines you to the green region, but if you use the two together, how come you get such a real improvement? Any ideas about why that might be? Well, the reason is that we've done two operations here. For the blue contours, we've basically marginalized over all the other variables, all the other parameters in the problem. When we combine the data sets, what we do is to multiply the likelihoods together in this high-dimensional space, and then marginalize. Now the operations of multiplying in a high-dimensional space and then marginalizing don't commute. So what we can't do is to marginalize and then multiply the likelihoods. So if you take these two Gaussian functions, bivariate Gaussians, and multiply them together, you will not get the red circle. So by I, you look at it and you think, that's what you do in your head. You take the blue bit and the green bit and you multiply them together and you don't get the red thing. But what you have to do is to do the multiplication in the high-dimensional parameter space and then do the marginalization. And then, as I say, those operations don't commute. So very often you do better than you think you're going to do because of that. Okay, what other things can we do with Fisher matrices? Well, I've spoken in terms of likelihoods, but if we want to, we can do the same exercise with posteriors if we specify a prior. So we can add a prior to the Fisher matrix, in which case it would then be referring to a posterior. So one very simple way to do that is that if you have some prior information on each parameter, which is uncorrelated with each other, you have some variance that's come from previous experiments, then you would just simply add to the Fisher matrix, you would add to the diagonal elements, you would add 1 over the variance of the parameters. So that's something that you might like to specify simply as a prior, just to say, I'm going to assert that that particular parameter has, before I have any data, that has a Gaussian distribution with a variance sigma I. Or it could be that it's come from a previous experiment, in which case, in general, the Fisher matrix would not be diagonal. You'd normally have some correlations between the parameters from a previous experiment. So, you can take the essentially not the Fisher matrix, but the Hessian matrix from the Planck chains, for example, and use that as a prior for a future experiment. So you would add in the whole of the Hessian matrix as a prior for the next experiment. And you add it in because, of course, the posterior is likely times the prior. So for the Fisher matrices, because it's a logarithmic object, then you would add in. Let me just mention one or two practical issues. If you're doing this for for Gaussian distributed data, this is the object that you need to calculate. Not necessarily trivial to calculate, even very simple things can be tricky. To do this, you need to take derivatives of the covariance matrix, and you need to take derivatives of the mean signal. So you would normally do that by finite differencing if your theoretical model is coming out, say, from CAM or some other piece of software. So there, in many cases, there are not analytic expressions for these derivatives, so you need to do it by finite differencing. I would just say be careful, because that's a more difficult operation than you probably think it is, and it's quite easy to get it wrong. The one that I generally use is a thing called a 5-point stencil. So you could just take 2 points and then just take the difference between the two values of whatever it is and divide by the difference in the parameter. That's not a very good way of doing things. It's better to take 5 points and then approximate the derivative by this linear combination of the 5 points around the point of interest. What I would say is use this, but also check the sensitivity to the step size. If you make the step size too big, then the function may not be linear over the range that you're looking at. If you make it too small, then you end up subtracting numbers which are very close to each other, subtracting 2 large numbers and dividing by the difference in h also gives you numerical problems. So explore this as a function of h, and you'll probably find that if h is really small, it becomes really noisy, and then it settles down to something that's stable. And then if you make the step size really, really big, it'll drift off because it's not linear over the range of h. So do a few and make sure that you're in a region where it's stable. Okay, other things to say are that you've seen many Fisher matrix plots with all of these ellipses. How do you produce them? Well, there are ways to do it. There are some tools that can help. There's a thing called Fisher.py. I've not used it, but I think what it will do is if you have your matrix in Python, or Fisher matrix in Python, it will no doubt take it in and spit out these block plots in a nice, convenient way. Just a couple more slides on this before I hand over to Licio. These things can be quite powerful for other reasons as well. If you have an experiment where some of your parameters are the parameters of the problem that you're interested in, but other ones are nuisance parameters, some systematic, to do with systematic errors or something, then if you make a systematic error so that one of your parameters is systematically wrong, then you have to be a little bit careful because it also affects the other parameters. So let's say that we have a 2-parameter system like this, where the true solution is here, say, but for some reason, the parameter here, which might be some calibration parameter, let's say, if you've got it set to the wrong value, then because the likelihood surfaces in general don't line up with the axes, then if you make a mistake in one of the parameters, then it will shift the expectation value of the other parameter. Now with the Fisher matrix, because you have complete control over this, you can actually work out what this shift is. So if you make a mistake in one of the parameters, which is size delta psi, zeta here, then all of the other parameters will get shifted systematically by an amount which is given by this expression. I haven't told you what this matrix is, but if you ever need to do this, you can find it in this paper. It's also of use if you're considering models that some models which are simpler versions of others. So if we consider, say, two models, one is lambda CDM, and the other is flat lambda CDM. So flat lambda CDM has omega curvature equal to 0. So if we worked out the Fisher matrix for the general lambda CDM model, and then specified that for the flat CDM, that omega matter had to be 0, omega curvature had to be 0, then that would actually affect the expectation values of all of the other parameters. So don't assume that if you do an analysis with full lambda CDM, that the results that you get for the values of the cosmological parameters are going to be unchanged if you then want to consider flat lambda CDM. So all of the parameters will change. And you can work out using this, using the Fisher matrix here, by how much they will have shifted. So that could be quite useful. Let me finish by mentioning more sophisticated things that you might sometimes find useful. You always get elliptical contours with the Fisher matrix because it assumes that the likelihood surface is Gaussian shaped. If you want to do better than that, you can use a thing called DALI, where you expand the likelihood surface to higher order. Just written here, expanded to fourth order in the parameter differences. And DALI is a way to give you an approximation to the probability surface that has a number of nice properties. It's a genuine probability distribution, so that it's positive, it integrates a unity, and it approaches the true distribution as you include more terms. So it's a bit more complicated to use, but I think there is software that you could use to that's public. So you would just give it your covariance matrix and your mean, and it can give you a better version of a Fisher prediction. So this shows you an example from supernova data from this paper, showing what, so the coloured parts here are the true shape of the likelihood surface. The Fisher approximation will be the ellipses here. If you use DALI, I think this is maybe including the second order terms, second order expansion terms, and third order expansion terms. You see that you get a much better prediction if you include these extra terms, but it's more work. Okay, so just to summarize, Fisher matrices are useful in experimental design. You don't need to have any data. You don't need to generate any data with a simulation. That might be expensive to do. And they are a good way to give you a first indication of how well you're going to do. The errors that you get, one thing I didn't mention is that the errors that you get are at least as large as the Fisher errors, called the Cramer-Rao result. So you may not do as well as you'd expect with the Fisher analysis. You may well do worse. It's quite easy to mess up. But I think, so this is a sort of one-way test, really. If you find that the experiment that you're going to do, if you do a Fisher analysis, and you find that the error bars and the quantities that you're interested in are 50 times larger than what's already known, then it's a pointless experiment. If they're much smaller, then that's probably a good experiment, but you may not get as good, quite as good an answer as you get predicted. Be careful with the numerical derivatives, and just to remind you that it's almost always the inverse of the Fisher matrix that is what you need, and just to remind you of the fact that covariance matrix of the parameters is the inverse of the Fisher matrix, and you're going to use that later on today. Okay, so I'm going to stop there. Are there any questions on that? If not, I was planning to hand over to Leacher, but I don't see you. Break. So we're all right. We'll have a 5-minute break and then.
Yes, we could have a break.